joining our second last SNAPP seminar of this year. So I'm excited to have Ziv Ziv today. So Ziv is an assistant professor at Cornell ORIE, and Ziv has received PhD degree in from CMU in 2022, and before joining Cornell, Ziv was a research fellow at Simons Institute at UC Berkeley and a postdoc at Harvard SCAS and MIT CSAIL. And Ziv works on the theory of stochastic control and decision-making under uncertainty, especially in queuing context. So, and his works have been recognized with multiple awards from Informs, ACM Sigmatrix, and IFIP Performance. All right, without further ado, the floor is yours.
All right, thank you for the introduction. And thanks so much for the invitation. I'm really excited to be here. It's really great to see lots of friendly faces in the audience. And I have some work that I'm really excited to tell you all about. So today I'm going to be talking about scheduling to optimize tail latencies, which has been one of the things that I think started bothering me about on like the second week of my PhD, approximately. And so I'm really excited to have a piece of progress on this to share with you all. And so this is joint work with two of my PhD students, George Yu and Amit Harlev. So we're going to study kind of a fundamental question in queuing, which is how should we schedule jobs to minimize delay? So first, let's just get oriented with what this means. We're just going to stick to single server queues today. We've got jobs arriving over time. I'm going to represent jobs as test tubes, where the height of the test tube is the size. That's how much time it needs to be served. And we've got jobs arriving over time. And the main thing we're concerned about is delay, sort of how long it takes a job to make its way through the system. So we're going to call this quantity response time, denoted T. Okay, so T is the amount of time it takes a job between entering the system and leaving. And the kind of big question is, okay, how do we schedule to sort of like keep response time small? And so this could mean many different things. So like an easy version of this question is how should we schedule to minimize average response time? And the key idea is serve short jobs before long jobs. That's basically the one trick we have in scheduling. Serve short jobs before long jobs. And for minimizing the mean, it turns out you just need this trick. And so if you always prioritize the job of least remaining size, including if a new job arrives, you might, if a new job arrives that has less remaining size than the one in service, you should switch it out, switch the one in service out for the new one. And basically doing this at every moment in time gives you a policy called SRPT, or shortest remaining processing time. This is always serving the job with the least work left. And this minimizes the average response time. Okay, but the average is only one of many possible metrics we could talk about to do with response time. Okay, and one really important class of other metrics is what I'll call broadly tail metrics. Okay, so these are things that have to do with the distribution of response time. Things like, what's the probability that the response time exceeds some threshold? Or you could think of that threshold as like a deadline, that I want every job to finish within 100 milliseconds in a computer system, or perhaps several minutes in like a service system. So that would be sort of the probability of missing a threshold deadline. Or you could ask about what's the expected amount that an average job exceeds its deadline. That would be expectation of big T minus little t positive part. Or you could talk about percentiles or quantiles of T. Okay, and usually we care about the case where, often we in practice care about the case where, we're trying to prevent large response times. And so, if you ask any computer systems practitioner, they're always talking about T99, the 99th percentile of T, right? Or there's, lots of companies have done studies that show that, hey, if their load times exceed some threshold, they lose money, or people close the window, or things like this. And so people, love tail metrics in practice. That's what they really want to optimize, but they're really hard to attack in theory. And this is even if we make sort of very mathematically generous assumptions that sort of allow us to do lots of things mathematically. So in particular, I'm going to study the MG1 today, which is where we sort of make what I'd consider kind of the maximum assumptions that are kind of reasonable for modeling at least a wide variety of computer systems. So I'm going to assume that, the job arrival process is as nice as possible in terms of times. So the arrival times are Poisson, but the job size distribution could be any distribution, but still each job size is IID. Okay, so this is like the nicest stochastic assumptions we could make without, without maybe super duper simplifying the problem. And it's still a really hard problem. And so what is tractable to study in theory is to study basically the large threshold asymptotics of these first two tail metrics, or equivalently quantiles very, very close to one, asymptotically close to one in some sense. And so that's what our work is about. It's about optimizing these tail metrics in this T to infinity asymptotic regime. Okay, so what does optimizing tail asymptotics look like? So let's start with the definition. This is basically going to be the kind of competitive ratio of a policy with respect to tail asymptotics. Okay, so I'm going to call this R pi. So here, if pi is a policy, R pi you should think of as, basically the ratio of is my mouse visible on the screen? Sorry, I forgot to ask. Okay, good. I see some thumbs up. Thanks. Okay, so here we've got our policies ratio. And in the denominator, we have like, what's the best possible, our policies tail. Here's the best possible tail we could get, for any policy, even one that's specifically tuned to this time t. And then we're going to take a limit of this ratio. And the sort of limiting ratio, this is kind of the asymptotic competitive ratio of our policy. And so we can ask, okay, obviously we want R to be small. Let's start with, we might ask that R be finite. Right, and this is called a policy being weakly optimal. A policy being strongly optimal is when R pi equals 1. So what policies are weakly optimal or strongly optimal? It depends a lot on the setting. So in particular, they're kind of broadly speaking, two types of queues you can be in the MG1. You can have heavy tail job sizes or light tail job sizes. I'll make these a little bit more precise a bit later. But for heavy tailed, you should think something like Pareto, and for light-tailed, you should think something like exponential or Gaussian. Okay, so what policies are weakly optimal in the heavy-tailed setting? Let's start there. Well, there's actually a lot. Here's an incomplete list. So things like preemptive last come first served, SRPT, previously appearing in this talk, also processor sharing, least attained service, and some other classics. And so these are all known to be weakly optimal. And the question, so as far as I know, the question of whether any of these are strongly optimal is somewhat open, but we were able to, kind of using a result of Adam and Bert's, we were able to show that at least in some, for regularly varying, a bunch of these do achieve the best constant. And it's like I'm not going to go into the details, but it's basically the constant everyone expects, the 1 over 1 minus rho thing, if you know. Okay, so this is to say that the question of optimal tail scheduling for heavy tail sizes is pretty much solved, at least for this certain class of heavy tail distributions. And in particular, we noticed that SRPT, which was good for the mean, is good for the tail. Okay, so we're done with that. How about light-tailed sizes? And that's what really most of this talk will be about. So for light-tailed sizes, for some time, the only known weakly optimal policy was first come, first served. So SRPT, processor sharing, and so on, not optimal for light-tailed sizes. You need to do first come, first served. And it was conjectured that first come, first served might even be strongly optimal. And so this conjecture stood for, I guess, a bit less than a decade, until Izzy Grossoff and collaborators, including Moore and me and Kunhei Yang, basically found a policy that was a little bit better than first come, first served. So it's called nudge. I'll explain nudge a bit later in the talk. But basically, nudge, we were able to prove that nudge has a better competitive ratio than first come, first served, for all but trivial cases like all deterministic, for like deterministic job sizes. So what this means is that first come, first serve is definitely not strongly optimal. But also the nudge work kind of revealed that there's a lot more to explore here. And so it's unlikely that nudge is strongly optimal. And so the question of finding a strongly optimal policy was left open. So that's what we do in this work. So we find we design a new policy called boost, and boost is the strongly optimal policy for light tail job size distributions. It achieves, R boost equals 1. And so this basically settles the question of how to schedule for tail asymptotics in the light-tailed regime. And so what we do over the course of what we do in our papers is, we basically show the design of this boost scheduling policy, we analyze its performance, and we show that that performance is strongly tail optimal for this light-tailed case. And let me sort of give a few more details. So boost isn't quite one scheduling policy. It's really more of a family of many scheduling policies. And by analyze its performance, specifically analyzing, roughly speaking, RPi, we analyze the boost performance for all instances of boost. And then we sort of identify one particular instance, which we call gamma boost, which is the strongly tail optimal one. And so for today's talk, I'm going to focus almost entirely, I think, basically, aside from one remark, I'm going to assume that we're in the setting where we know job sizes. So that is to say, we're scheduling with exactly the heights of the test tubes visible. We can see how much work we've done, how much time is remaining, and so on. And so this problem was open in the known size regime. And by sort of demonstrating gamma boost for the known size regime, this is basically the best you could possibly hope to do in the MG1. In fact, an artifact of our proof is that even if you knew like what the future arrivals would be, it wouldn't help. This gamma boost is really the best you can do. So basically this is in the sort of full information case. You could also say, okay, well, what if I don't know the job sizes, right? This is a very realistic setting. And in preliminary work, which we're going to present at the MAMA workshop at Sigmetrics in just a very small number of weeks, I think less than 2, at MAMA soon, we're going to show preliminary work on basically an unknown size version of gamma boost. And a small spoiler alert, it turns out gamma boost is secretly a version of the Gittins index policy, but with some weird twists. So more on that later, perhaps mostly during questions, because I think we're going to have lots to talk about with just known sizes. Okay, so this is kind of what we do. So here's a kind of overview of the main questions I'm going to focus on in the rest of the talk. So first, you're probably wondering, okay, what is this family of policies? How does this boost family work? And how do we use it to achieve strong tail optimality? And I will get to these questions. And it turns out the answers to these are actually not that complicated. And so I want to start by focusing on a question, which is, given that the answer ends up not being so complicated in the end, what makes this problem so hard? Because this is a really hard problem. It was open for some time. And basically there are some big difficulties that occur in the light-tailed setting that don't occur in the heavy-tailed setting. And so I'm going to talk about those. So to get started on why is achieving strong tail optimality hard, I want to go into a bit more detail about what heavy-tailed versus light-tailed scheduling looks like. Okay, so a kind of very hand-wavy definition of heavy-tailed job sizes, you should think S is roughly Pareto. Okay, and a very hand-wavy definition of light-tailed job sizes, you should think S, the job size distribution, is roughly exponential or maybe lighter. Okay, if you know what regularly varying or class 1 means, those are the specific assumptions I'm talking about. Okay, so in the heavy-tailed world, if S is roughly Pareto, that means that for basically any reasonable policy, the response time is also going to be roughly Pareto. And similarly for exponential, if your job size distribution is roughly exponential, then your response time tail is also going to be asymptotically exponential. And so the parameters here, so we've got in each of these expressions, we've got a leading constant C, which I'll call the tail constant. and we have some exponent gamma, which I'll call the decay rate. That term is more common in the light-tailed setting, but just to use the same word, I'll say decay rate for heavy-tailed as well. Okay, so we've got the decay rate and tail constant. And basically, you should think of the decay rate as basically saying, on what's the order of decay of the tail. And so weak optimality is, okay, it should say maximizing gamma, right? You want it to decay as quickly as possible. Okay, and then strong optimality should say maximizing gamma and minimizing C, right? You want to decay as quickly as possible, and then subject to decaying as quickly as possible, you want the leading constant to be as small as possible. And so in particular, if you have a policy such that gamma pi is the best it can be, then R pi is just the ratio of your policy's tail constant to the best possible tail constant. Okay, so if we're aiming for strong optimality, well, we got to get through weak optimality first. So let's talk about what policies achieve what decay rates. And so I'm going to start by comparing kind of two families. One is the family that I told you was optimal for a heavy-tailed setting. That's SRPT, least attained service, and so on. And then the other is first come, first served, which I told you is weakly optimal for the light-tailed setting. Okay. And so, and one curious fact about these is that actually, even, first come, first serve is optimal for light-tails, but it's actually the worst you can possibly do in the heavy-tailed setting, right? And this is a sort of standard fact. It's a sort of well-known fact in queuing that if you have highly variable job size distributions and you do first come, first served, you're going to have a bad time thanks to the inspection paradox. Okay, and that's exactly what happens. If you know the details of the inspection paradox, you'll see why it makes sense that you get a difference of 1 between first come, first served's tail constant and the optimal. Okay, so we kind of know first come, first serve. It's well known that first come, first serve is a bad idea for heavy tail job size distributions. Perhaps it's a bit less well known that SRPT is actually the worst you can possibly do in the light-tailed case. All right, so this is and in fact, this is an either-or situation. So Adam and Bert showed that any policy that is optimal in one of these settings is basically decimal in the other. So what is this? What's the cause of this big difference? And the cause of this big difference is that each of these settings, the heavy and light-tailed setting, really has a different main cause of having large response times. So in the heavy-tailed case, we've got the catastrophe principle, right, which says that we're failing because there's one giant job. And so we can sort of ask, okay, how does this one giant job manifest in the decay rates of SRPT and first come, first served? So in the case of SRPT, notice this decay rate gamma is the same as alpha, the job size decay rate. So what's this saying? This is saying that like the exponent is the same for the job size distribution and the response time distribution. And the reason this is happening is because the sort of jobs that have the worst time and the jobs that sort of contribute to the asymptotic tail are the giant jobs under SRPT, right? So under SRPT, if you've got a job that's taking a super duper long time, it's because it's a super duper giant job. And yes, that super duper giant job takes a long time, but all the little jobs get to pass it. Whereas if you were doing first come, first served, the giant jobs would have a somewhat better time, but now you'd have loads and loads of jobs stuck behind the giant job. And because there are so many more non-giant jobs, having lots of jobs stuck behind the giant job ends up being a worse deal than just having the giant jobs take a long time. And so those are the sort of causes of large delays in the heavy-tailed case. How about the light-tailed case? So in the light-tailed case, rather than sort of having a sort of catastrophe phenomenon for large deviations, you have the so-called conspiracy phenomenon. So that is to say, when you have a really long delay in light-tailed setting, it's because you have lots of biggish jobs. And specifically, you have some period of time where you have a slightly higher than average arrival rate and a slightly bigger than average jobs showing up for extended length of time. And so what happens when that happens? So you end up with lots of work in the system. So the work in the system is the sort of total remaining size of all the jobs in the system. So under first come, first served, when you walk into the system, your response time is going to be your own size plus whatever work is in front of you. And so large delays in first come, first serve happen when you see lots of work. In contrast, under SRPT, least attained service, large delays, lots of work can contribute to the delays, but the bigger contributor is when, if you're a giant job, or even just not maybe there aren't giant jobs really, but a very big job in the light tail case. If you're a very big job, then lots of smaller jobs are going to pass you. And if you have one of these situations where, somewhat more than average jobs are arriving for an extended period of time, and those jobs happen to be a bit bigger than average, this is going to lead to a sort of really long delay, a sort of like temporary starvation for that very big job. And it turns out that this ends up giving you kind of the worst decay rate, because these very big jobs sort of finish at the end of the busy period. That's sort of like the last moment possible before the server is about to be idle. So they get saved for last. They have a really bad time. Okay, so we've got these like two very different pictures of what causes large delays in these two settings. And so we might ask, okay, so it looks like, it's really hard to kind of prioritize small jobs and still have a good time in the light-tailed setting, right? SRPT prioritizes small jobs, gets pesimal gamma. But remember from the beginning, like serving short jobs in front of long jobs is basically the only tool we have in scheduling. So, what might we try and do instead? So one idea might be to say, okay, how about if you take SRPT, or least attained service, or let's just focus on SRPT for now, right? If we take that and we don't do full SRPT, maybe we just divide jobs into two buckets, small and large, right? And we prioritize the smalls over the larges, right? But we don't sort of prioritize amongst the larges, and we don't prioritize amongst the smalls. The hope is that, this might make it so that, we don't get sort of as extreme starvation. So, you could ask, how does this do? So unfortunately, this doesn't really solve the problem. So first, in the heavy-tailed case, it turns out this is also pesimal. And you don't sort of get that much back for being pesimal in the heavy-tailed case. Turns out this will have an intermediate gamma between the pesimal and optimal values. If you're interested in the details, basically what you have is you have a busy period started by effectively the full work in the system, but with a truncated job size distribution. And that's going to give you sort of a decay rate between the full busy period decay rate and the workload decay rate. And so what's the kind of cause of these, what's the intuitive cause of these long delays? It's when you're in bucket 2 and there are lots of bucket 1 jobs passing you, right? That's not as bad as the case where, you're very big and any job that's smaller is passing you, right? At least it's restricted to bucket 1 jobs passing you, but it's still a lot. So it's still going to give you bad decay rate. And so kind of focusing in on this light-tailed case, which is what we're talking about today, the main takeaway is that to achieve strong optimality, even just to achieve weak optimality, we must avoid strict priorities. And that's difficult to do, given that prioritizing short jobs ahead of long jobs is the main tool we have, right? And if we hope to improve upon first come, first serve, we need to introduce some amount of prioritization of small jobs over long jobs or something like this, without getting even slightly too much towards SRPT. Even just 2 buckets is already bad. Okay, so given all this, can we even beat first come, first serve? So I'm going to draw an example where I basically explain there is a way to beat first come, first served, known in prior work. It's called nudge. And it takes this idea of, okay, we're trying to avoid strict priorities, but we still want to serve short jobs in front of long jobs. It sort of takes this idea to the extreme. So here's what I mean. So let's say we've got, some work in the system and a long job arrives and then a really short job arrives. So nudge says, well, I want to slightly nudge short jobs towards a better time. So I'm going to let small jobs pass one large job. Okay, so that means that nudge is going to, when this small job arrives, Assuming this large job is still in the queue, it'll switch these. Okay, but then we can't go even slightly towards SRPT, right? And so nudge sort of has a very conservative failsafe, which is once a large job gets nudged, it can't be nudged again. A large job can't be passed twice. So we sort of mark this job as nudged. And so if a new job arrives, even if it's super small, we're not switching it. Okay, and so there's some details about, okay, how do should you define short versus large? Basically, any threshold works. And for basically, as long as you choose the threshold in a reasonable way, what you get is that the sort of tail constant of nudge is strictly less than that of first come, first served. Okay, just by doing this occasional nudging of one short job in front of one long job. Okay, and the question you might have is, okay, is there anything special about one? What if you nudged twice? Or you could have like maybe a short job can go ahead of lots of longs, but a long can't be passed by lots of shorts or something like this. And so there are many more complex variants have been studied recently by Benny van Hout and Niels Charlet. And they basically, in fact, found pretty much the optimal way to nudge, to do nudge in their latest paper, which is a preprint on archive. And so that's the story with nudge. And actually, the if you look at the sort of C nudge versus C first come first served, in our initial nudge paper, the improvements was pretty modest. The latest from Benny and Nils is actually a lot better. So nudge can take you pretty far. All right, but we want strongly optimal. So we beat first come first served. Can we beat nudge? And I think the sort of main thing that the sort of the state of the art in nudge right now, the main drawback it has is it buckets jobs into short and long, right? And so if we can answer this question, how do we handle a range of job sizes? Then, we have a good chance of being able to improve upon nudge. So let's say we've got this situation where this long job arrives first, a medium job arrives second, and a short job arrives third. How should we schedule these? Should we treat the medium job as, sorry, this should say small, right? And thus treating the medium as small, we'd swap it with a large job. Or maybe the other way around, this should say medium is large, right? So should we treat the medium as a large job and thus swap the short job in front of it, right? Or maybe we should do something else, right? Where we could even sort all of these three jobs, right? And as long as we don't go too crazy, maybe we can do better than nudge without, decreasing our tail constant. So it's really not clear how to answer this question. Beyond, and the state of the art right now is basically to design nudge-like policies, analyze them, and then optimize their performance either numerically or in some of the latest results from Nils and Benny, they show that amongst this class of nudge policies, here's the best you can do. But I think we're still kind of missing sort of what's the principle we should use to decide between these three situations. And I'm going to come back to this, but the idea I'll plant for now in your mind is it turns out each of these situations is going to be best in different cases. And so I might ask you, what extra information would help us decide which of these cases we want to do? All right, so that's seed number one I'm planting. All right, here's a second seed. So, okay, so we want to beat nudge. We have this vague idea of like what we should do, but it's kind of hard to figure out how to proceed. So another approach we might say is we could just sort of directly try to find the optimal policy. Okay, so and so if we're looking for an optimal policy, we have to ask, where do optimal policies come from? Just broadly in queuing, right? If we've got some queuing problem, we have some jobs, we have arrivals, how do we find an optimal policy to minimize some metric, right? And the thing about queuing problems is that they have these pesky arrivals, which make things really difficult. Whereas there's a lot of scheduling work in the sort of a more theoretical computer science flavor that studies lots of batch problems, where you just have some set of jobs and you have some metric, which might be directly analogous to a queuing problem, right? For example, maybe you're trying to minimize the average response time of this batch of jobs, where you say they all arrive at time 0, or maybe they had some past arrival times, but you're sort of being dropped in media res, right? And you have to deal with what you have. And you're trying to minimize average response time starting now. And if you sort of do a batch version of minimizing mean response time, you get SRPT. And it's not a direct, solving a batch problem doesn't necessarily mean that you've solved the queuing problem, but it's at least a place to start, right? That's one place optimal policies can come from. And indeed, as we shared on the first slide, SRPT is also optimal in the queuing version. And so this prompts a sort of a complementary question, I think, which is, what's a batch version of minimizing the tail constant? Right, that would be one. If we're trying to sort of, if we have this fruitful source of potential scheduling ideas in batch scheduling, right? Things like SRPT, things like the CMU rule, and so on. All you can GITINs, you can think of these all as coming from batch problems. But minimizing the tail constant is this asymptotic thing, which really requires like infinite sequences of arrivals for the limits to make sense. And so the kind of question that's going to be key to figuring out a batch version of the problem is, how can we find a non-asymptotic version of the tail constant metric? And basically, as to the best of our knowledge, there isn't any sort of there hasn't been any studied in the literature anything like sort of a batch problem that's related to tail scheduling. All right. And so I think that these two reasons, right, the difficulty of handling a range of job sizes and doing some sort of intelligent priority without devolving into SRPT or SRPT with buckets or something like this. That's really hard. And we don't have that many things in queuing that look too much like that. And so the fact that it's hard to handle a range of sizes in the light-tailed setting, and it's also hard to use traditional methods like going to a batch problem, it's hard to do that for asymptotic metrics. I think that's why achieving strong tail optimality is such a hard problem. So what I'm going to do in the rest of the talk, so maybe first I'm happy to pause for questions before getting to the second half of the talk, where I'm going to talk about what boost is and how it achieves strong tail optimality. And we're going to see basically answers to both of these questions of how to handle a range of sizes and a batch version of minimizing the tail constant. But first, now is a good time to pause for questions. So I'll take 10, 20 seconds.
So just one quick one, Ziv, please.
Yeah.
You've mentioned that part of the issue is sort of relative to these humongous jobs, just their service time themselves, is that could be driving on some of these delays. Could you look at a normalized metric, something like the response time divided by the job size?
Okay, this is a great question, which is, should you think about slow down or stretch, right? Response time normalized by job size. And so I think this is actually the next metric to study. Right now, I don't think we know very much. I can comment a little bit at the end of the talk. Basically, we know something which is maybe up to, which is not, I don't think we even know a weekly competitive, at least by the definition in this talk, policy for that. Although we do know, at least I think we know, at least for some settings, a kind of something that is a slightly bit weaker because of some work from Stoliar and Kavita Ramanan about sort of weighted delay, prioritizing by weighted delays. It's sort of like a generalization of first come, first served. Let me talk more about this at the end if you're curious. But short version is, I think right now we don't know how to do that to the same degree as response time.
I have a quick question. So you're assuming you know the job sizes. So you actually know the work when a job arrives, right? So a job could make its decision based on the work that it sees. right?
That's
I mean, in terms of meeting
totally
a deadline,
right.
that's something that it could use. Okay.
Yes.
All right. I'll keep thinking about that because that
Yes.
seems like a tool that a job could use in determining what to do. All right. Thanks.
So this, sure.
Sorry, I arrived a little late, but do you know the distribution?
Okay, good question. We are going to assume that we know the distribution. However, what we really just need to know is the optimal decay rate, gamma. So like in the decay of the workload, namely the pole of the transform, we just need that number. And so if you can estimate that number from data, then that's going to be good enough. Also in the paper, we do some empirical sensitivity analysis, and if you get it wrong, it's basically fine. For the unknown size version in preliminary work, you definitely do need the distribution, though. Okay, so let's talk about how the boost policy family works. And so how does boost work? Let's start with this situation that we were looking at just a few minutes ago, right? We're trying to handle a range of job sizes without devolving into something like SRPT. All right, and I gave you a hint that if you look at this situation where this job arrived first, this one arrived second, this one arrived third, there's a key piece of information that is going to help us decide how to order these jobs. Okay, and that key piece of information is I've shown you the order the jobs arrive, but I haven't shown you when they arrive. And if you think about when they arrive, if you use the arrival times, that might help you make the decision. So for example, suppose that this long job arrives, a long time ago, and then the medium job arrives very shortly after the long job. And then a long time passes, and then after a long time, the short job arrives. All right. When it comes fine, maybe there's some work ahead of these, and that takes a while. When it's finally time to serve, one of these three jobs, the long job has been waiting much longer than the short job. The medium job has been waiting almost as long, right? And the short job has not really been waiting quite as long. And so it might make sense here to say, well, the long and the medium have been waiting almost the same amount of time. And in general, I should sort of be biased towards serving shorter jobs first. So maybe it makes sense to switch the medium with the long in this situation. But you could easily imagine other situations where you do something else, right? What if the long job arrived a really long time ago and the medium and the short showed up more recently, right? Then you might say, well, the short and the medium arrived at almost the same time. I should be biased towards the shorter job, so maybe I'll swap the short and medium. But this long job has been waiting a long time, so I'm going to do that first, even though there's a shorter job in the queue, just because the long job has been waiting so long already by the time I get to these, right? And maybe if they're clustered all together, that's when you would just say, all right, these arrived at almost the same time, right? It's sort of, they've been waiting for such a similar amount of time that my bias towards short jobs should win over sort of being worried that I'm keeping someone waiting for too long. Because maybe had things gone just a little bit differently, they would have arrived in another order. So this is just some vague intuition for why thinking about arrival times should inform your scheduling decision. And this is something that basically Nudge doesn't directly do. The kind of most successful versions of Nudge from Nils and Benny, the latest versions kind of secretly, implicitly use arrival time information by thinking about sort of how far apart in the queue two jobs are. But if you're in a system where you can actually, keep timestamps of when jobs arrive, you might as well use the actual arrival times. Okay, so we have this idea that we should use arrival times to somehow handle this range of job sizes. So how can we somehow combine arrival times and job sizes to get some sort of priority? And so the way boost policies work is they combine arrival time and size in a very simple way to get a priority. We call the priority a job's boosted arrival time. And a job's boosted arrival time is its true arrival time minus a quantity we call its boost. Okay, and the boost is going to be a function of the job's size. All right, so the way to think about this is that when a job when a job arrives, the priority we treat it as is it's kind of like we pretend it arrived earlier than it actually did. All right, so the job kind of boosts forward in time, right, as if it had arrived earlier. And so we use these boosted arrival times to decide which job to serve next. So just as first come, first serve is always scheduling the job of least true arrival time, boost is always scheduling the job of least boosted arrival time. And the key idea is that you should give smaller jobs bigger boosts, right? So if you have a small job, it should get a really, really big boost and go really far ahead, potentially skipping past lots of bigger jobs in its way. Whereas a big job should get a pretty small boost, right? Maybe skipping over a couple of super big jobs in its way, right? But only if they arrived like really close by. Okay, so just to sort of kind of be just to clarify exactly what the class of boost policies is, right? Boost policy is basically anything that can take this form where you're always serving the job of minimum boosted arrival time, where the boost is a function of the size. And so what does this end up looking like? Well, let's kind of consider a situation, like one of the ones we saw a few slides ago, where we've got a long arrives, then a medium arrives, and then sometime later a short arrives. We might boost all of these jobs some amount. And, the idea of kind of boosting smaller jobs a bigger amount naturally leads to some sort of interleaving that that compromises between serving jobs that have been waiting a long time and serving short jobs before long jobs. Now, of course, the big question is, okay, well, what should the boost function be? And so exactly what this boost function is the main knob you have to tune when designing a boost policy. There's also some details about you could do preemptive or non-preemptive versions of boost, but it turns out it doesn't affect the tail constant. So I'm not really going to worry about preemption today, right? But the big question is, how should you decide what the boost should be as a function of the size, right? Any function boost of size that you choose will give you some boost policy, right? But only one of them is going to be tail optimal. Okay, but that's the basic idea of how the boost family works. And so how do we achieve strong tail optimality? So let's start by asking, well, okay, again, before getting to strong optimality, we got to get through weak optimality. All right, so let's start by asking, is boost even weakly tail optimal? And the answer is going to be yes, but not always, or mostly, but not always. So, so this last sort of quarter of the talk is going to be sort of more math heavy than the others. So brace yourselves. So let's remember that we're looking at, in this light-tailed case, our response time distribution is asymptotically exponential. And so let's write out, what a formula for that tail constant is, right? This is just sort of rearranging the asymptotic expression to extract C as some sort of limit. And, in queuing theory, we love Laplace transforms. And so it makes sense in moment generating functions. And so it makes sense that we might want to express this limit in a different way that uses moment generating functions. And so these two limits are equivalent by final value theorem. And kind of our first key idea, roughly speaking, is we're only going to think about the Laplace transform version. We care about tails at the end of the day, but all of the thinking we're going to do about how to get a good policy is going to be in the Laplace transform land. So okay, we want weak optimality. That means we need C less than infinity, right? So let's first just ask, what does a weakly tail optimal policy look like? Well, we know first come, first serve is weakly optimal, right? And under first come, first serve, a job's response time is the sum of two parts. It's size, S, plus W, the amount of work it sees when it walks into the system, right? Because it has to wait behind all that work. And so what does the tail constant of first come, first serve look like? It looks like, well, basically when you take this limit, what ends up happening is that you get some constant from the amount of work. We're going to call that CW. And then sort of something, and then the plus S ends up just falling out as an extra factor. And so the way to read this is that, just like how you multiply moment generating functions whenever you add independent random variables, basically the same thing works for these limits of moment generating functions, provided that sort of only one of the moment generating functions is sort of exploding, as long as only one of the summands has an MGF that's exploding to infinity. So here the W MGF explodes to infinity, the S MGF converges to some finite value, e to the gamma S. You can, I should mention that for the rest of the talk, gamma is the sort of optimal gamma achieved by first come, first served, and also under a lenient condition we'll get to in a second, boost. So gamma is that sort of pole of the work MGF. Okay, so this is basically what first come, first served looks like and where its tail constant comes from. So what does boost's tail constant look like? Well, first, let's ask, what does boost's response time look like? So in our paper, we don't have an exact analysis of boost response time distribution. It's basically too hard. But we do get upper and lower bounds that are tight, that sort of match in this sort of Laplace transform limit. And what they say roughly is that a job's response time under boost is has some familiar terms from first come, first served with some differences. So it says, okay, it's kind of like you have to wait for the work in front of you, right? And you also have to wait for, and also you have your own size. But because you're being treated as if you arrived B of S time earlier, what effectively ends up happening is that you end up sort of, it's almost like you subtract B of S from your response time. Here, B is the boost function. Okay. So this is the gain you get from boost. Small jobs get a lot subtracted from their response time. Okay. But there's something else, which is that, there's this other term. So what's the cost of boost? It's something we call crossing work. And this is basically, well, you get to boost past jobs, but other jobs get to boost past you. And V is going to account for that. I'll draw a picture soon. Okay. But what this means is that basically C boost is going to be a similar product to C first come, first served. But instead of e to the gamma S, we have a smaller term, e to the gamma S minus B of S, where B is the boost function. But then we have an extra factor to do with this crossing work. All right, so let me talk about that crossing work for a second, because whether boost is weakly tail optimal is about whether this crossing work MGF is finite. And so what is crossing work? It's basically, let's pick an arbitrary point in time. So here I've drawn a bunch of arrivals. Imagine this is like the infinite sequence, both directions of arrivals. I've drawn each job, basically each job's boost arrow. So this job arrived here, boosted to here. And this job arrived back here, then whoop, boosted to here. So what is crossing work? Crossing work is if I draw at some moment in time, any moment will do by symmetry. So let's just say time 0 for concreteness. Let's say I draw a line at time 0. And I ask which jobs arrive after time 0, but boost to before time 0. And all of those jobs count as crossing work. And the reason why I get delayed by a crossing work amount is that if you think about, if I'm a job, if I walk into the system, my priority is my boosted arrival time. And so roughly speaking, this W is actually the work in the system at my boosted arrival time. And so you have to wait for all of that work, but BS of that work has been done already. And so and then the sort of extra work you have to wait for is, well, anyone who arrives after your boosted arrival time, but gets to boost in front of it, will contribute to this V term. And so why is this crossing work term sort of not too big a deal? Well, roughly speaking, it's that, if I look, these big jobs, right, which would contribute a lot of crossing work if they crossed, because they have such a small boost amount, they're only going to cross if they arrive very soon after. And in fact, the longer and longer I sort of go into the future, the smaller and smaller a job will need to be in order to boost past my dotted line. And so as long as your boost function doesn't boost small jobs a super big amount, you're going to be okay. And specifically, we prove that this MGF is finite, as long as your boost function is, this should say big O of 1 over S. So actually big O is fine. And so this kind of makes sense, right? You don't want to sort of, if you let small jobs boost a super big amount, you're going to be in danger of becoming something like SRPT. But you can boost small jobs quite a bit without hitting that. So that's weak optimality. And it also sort of suggests one way to sort of find an optimal boost policy, which is, we actually analyze this expression exactly. It's basically a use of Campbell's formula for non-homogeneous Poisson processes. So you could take this, and if you have a finite support job size distribution, you could try and do, you could try and kind of do calculus to it, or you could do calculus variations. And in fact, that does work, but I don't know if it's easy enough to do without knowing the answer already, because we used a batch problem to know the answer already. So how are we going to get strong optimality? We're going to find a batch problem. And the key to the batch problem is, just like with weak optimality and understanding the tail constant, is going to be all about this Laplace transform interpretation of C. And the kind of move I want to make is I want you to look at this limit and say, okay, what happens when theta reaches gamma? When theta reaches gamma, we have an indeterminate form, 0 times infinity, right? Because we have gamma minus gamma in the left factor, and we have e to the gamma t, which is going to be infinite in the right factor. Okay. But and so in some sense, minimizing C is kind of like minimizing e to the gamma t, with a small caveat that that number is literally always infinity for every policy. Right. But this e to the gamma t looks like something that we could reasonably turn into a finite batch problem. And so that's what we do. So we think about some finite batch of jobs where each job has some arrival time and some departure time. The departure time will depend on our policy, and we're trying to optimize the some weighted sum of these exponents of response time. Right. So here I've just said, if I've got some finite batch of n jobs, then the expected e to the gamma t of a random job is just this expression, right? I'm averaging the e to the gamma t's of all n of my jobs. And this is almost, and then I can sort of rewrite this by expanding what ti means as basically something to do with the arrival time and something to do with the departure time. And this is almost a classic problem with a known solution. So this is almost classic. So what's the classic problem it is almost? It's minimizing mean weighted discounted departure time. Say that 5 times fast. All right, so and what is mean weighted discounted departure time? It's something very similar, right? You have some weight for each job, and then you have e to the something to do with the job's departure time. Okay, and so we almost have mean weighted discounted departure time as the batch problem for minimizing C. There are a couple of important differences, though. So, for example, the discounting in the classic problem, we usually assume a negative discount rate, right? So that is to say, the sort of cost of a job is getting smaller and smaller over time. Whereas we have not really discounting, but inflation. And so that's one difference. Another difference is that here, we can interpret these e to the negative gamma AIs as weights, right? We could say, let WI be that. And then it would sort of the objective would look very similar. But the thing is, we actually also have an extra constraint in our problem, which is that AI is the arrival time, right? We can't actually start serving job I before time AI. And so what we do is, well, we just basically don't worry about either of these problems. So in the case of the can't start I before AI, we say, well, what if we consider the relaxation where we can sort of start a job from the future? We call this cheating. And so we solve and in terms of the gamma being bigger or less than 0, we actually go through the classic proof for mean weighted discounted departure time, which is solved by a policy called weighted discounted shortest processing time. And we basically just checked that the interchange argument still works if you flip the sign of the discount factor. There's like a couple of extra signs that flip in the proof, but it's literally the same other than that. And then by staring at the weighted discounted shortest processing time, by staring at the sort of priority index that that policy gives you, you take the log of it and you find that it's a boost policy, specifically with this boost function. And so what is this boost function? This is basically, it's kind of like B of S equals 1 over S, except with two differences. The first is that you have this gamma, which is basically telling you what's the relevant scale to look at, right? Because it makes sense that you're somewhere in your boost function should be some sort of unit that tells you what size 1 means. And so gamma is playing that role. And then the second thing is that instead of sort of hugging the axes polynomially, like 1 over S, this boost function hugs the axes exponentially. So that is to say, a big jobs boost decays to 0 exponentially fast. And also only the super duper tiniest jobs get really big boosts. And so this is the policy that we call gamma boost. And so actually, gamma boost, again, is a family of policies, though here literally just parameterized by one number, which you can get by sort of looking at your queue and seeing what does the workload in your queue look like. Okay, and then my one comment about unknown sizes is that just as WDSPT is sort of a well-known thing for discounted problems, but seems to generalize nicely to inflation, same thing happens for Gittins when you have unknown sizes. And so the workshop paper we'll be presenting in MAMA is about our initial progress on this. Okay, so that's how we achieve strong tail optimality. We look at this batch problem, we find the right boost function. Okay, and then we do a bunch of math, basically some monotone convergence theorems later, and you show that that basically you can get a lower bound by thinking about the batch problem, and that lower bound converges or matches the C boost that we get as well. So that's how we achieve strong tail optimality. Okay, and so strong tail optimality, it's a nice strong theoretical property, but it's also a theoretical property, right? It's all about the t to infinity limit of the tail. So you might ask, is this any good when you're not looking at the t to infinity limit? And for the purposes of this talk, I will give a one-word answer, which is yes. And you can see the paper for more details. Okay, maybe a few more words. The improvement is bigger, the higher the variability is. And the trend you'll see is that here, this is a plot of sort of tail performance. Higher is better. So 0 is first come, first served. 1 would be having a tail of literally all zeros. And this dotted line is the sort of asymptote. And so actually, we do better than the asymptote. Basically, it seems sort of like as early as possible. These other lines are other policies. Okay, but these figures and many more are in the paper, including a sensitivity analysis and some initial results about simulations with unknown sizes. Okay, and with that, I'll conclude my talk. So I'm really excited about this idea of boost policies, and I'm excited about it for a couple of reasons. From a practical standpoint, sort of boost, even if you're not using the optimal boost policy, right? Maybe you have your own criteria of exactly you want to prioritize this, but you kind of want to prioritize that, but you don't want to make anyone wait too long. Boost policies basically gives a sort of new knob to turn to give some priority while staying weakly tail optimal, right? Basically any non-very boosting boost policy will be weakly tail optimal. So I'm excited about it from that sort of practical point of view. And from a theoretical point of view, the fact that we were able to sort of get, such a strong result by looking at a batch problem and sort of makes me excited about sort of what other metrics are sort of waiting to be turned into batch problems or something similar from which we can extract, kind of policies that have practically state-of-the-art performance, like Boost does for especially really high percentiles. Okay, and so thanks for your attention. With that, I'll conclude my talk. Thanks again.
Thank you very much for excellent talk, Ziv. So, yeah, we have a few minutes for questions. Does anyone have? There's a question on the chat message. Slide 18.
Yes. So, yeah. Yes. So, so the question is on slide 18, is e to the gamma t infinity? Yes, e to the gamma t is infinity for every policy. So it's not literally like minimizing e to the gamma t. But what happens is e to the gamma t, it's a metric that doesn't make sense in the queuing setting, but it does make sense in the batch setting. And so basically it ends up giving us the right guess for the optimal policy in the queuing setting. Thanks for the question. Yeah, Rhonda.
Yeah, I'm just wondering, since you said that it seems to perform better when there is more variability, I wonder just empirically how it might work even when you have a heavy tail, so that you know it would be something that could be reasonable in both regimes.
Okay, that's a good question. We haven't looked at this empirically in the heavy tailed case. I do know that basically in the highly variable light-tailed case, things like hyper exponential with really large coefficient of variation, you get things like SRPT is better at the 99th percentile, and boost is better at like the 99.9th percentile. So my suspicion is you're going to still do better than first come first served, but I think in sort of truly heavy-tailed cases, this is probably not the right approach. Now, I suspect that going back to Shane's question about slowdown, I expect that's the right thing to think about next for truly heavy-tailed cases. The reason being that you don't see, like, the theory we have for heavy tails right now tells us to worry about the super duper biggest jobs, which like only slightly exist because any real distribution does eventually peter out. And so, but it sort of seems heavy-tailed for long enough that we want to somehow think of it as heavy-tailed. And so I wonder whether studying slowdown might sort of reveal some of these distinctions. Yeah, thanks for the question. Bert, I see you also have a question in the chat.
Yeah, you assume basically existence of this constant C for the workload W, right?
Yeah.
And there is also a situation where that C doesn't exist.
Yes. So
and I was wondering if boost is still optimal for that class of light-tail distributions.
Okay, great question. We don't know. And I've started thinking about this, and every day I wake up with a different opinion. But basically, so just some background on the question. There's basically cases where where you sort of can't use final value theorem to extract this leading constant C. And in fact, the tail is not exactly exponential, but is exponential with some polynomial factor. And this is important, I think, because it's going to show up if you want to minimize something like slowdown. Because if you want to minimize something like slowdown, you are going to want to have some amount of busy periods of small jobs going in front of large jobs. I don't think the same full busy periods as SRPT. The guideline is really Sasha Solyar and Kavita Ramanan's work on which basically shows that the right thing is an accumulating priority policy. And that's going to give you sort of a bit of busy period. And anytime you have a busy period, you have the potential to violate Cramer's condition. So, and so I think that while it is definitely a still remaining open question, and even if you think that it's maybe just a technicality from the perspective of, are you really going to have a job size distribution that's, exponentially damped, regularly varying? Well, maybe you won't have jobs that look like that, but if you have busy periods, they look like that. And so I think
guess you could go first. You could first ask yourself the more modest question: Is first come first served not optimal? Like people before you,
yeah,
I guess you were also
I don't know.
involved, like what you did was like a combination of a series of papers in a way, right? So you have to probably go through the same set of exercises again.
Yeah, I don't. One thing that gives me pause is that if you try and do some of the Tauberian theorems, you basically look at some derivative. You end up trying to minimize things that don't quite look like this objective, but they'll have like an extra factor of TI or TI squared. And I don't yet know if that's going to be nice enough to optimize. But
Okay,
I think it's a
really maybe one day we can talk about it.
Yes.
Offline. Okay.
Yes, let's.
Thanks.
Alireza?
Hey, thank you very much for the great talk. So I had one question. When all the jobs arrive together, there could be cases that you would do the opposite of SRPT. So I was wondering if there's any way that we could balance both the mean response time and the tail bound.
Okay, yeah. So yeah, I think right now we don't know what the Pareto frontier is of mean and tail constant. I conjecture that actually you can get arbitrarily close to both, but only for the sort of kind of disappointing technical reason that means aren't asymptotic notions and tail constants are. So this is a comment Moore made at some point in the talk. If you do SRPT while you have less than 10 billion work, and then you switch to boost if you have more than 10 billion work, you're probably going to be fine. And you know exactly what that means, you have to think about it. But I think that from a purely theoretical point of view, achieving both good mean and good tail is probably not so hard, although it might be hard to like formally prove. So with that said, actually, you know, when it comes to like what are the practical metrics, this is something that I think is going to depend a lot on the particular system. But you could do things like crank the boost a lot more than we're doing in the optimal case, in which case you'll remain weakly tail optimal, although perhaps with even a worse constant than first come, first served, but with mean comparable to SRPT. And that might be something a bit more realistic than, you know, pie in the sky theory. You can have both.
Got it. Thank you.
Izzy, or do we have time for?
Yeah, so.
Okay, yeah, Izzy.
Okay, so Steve, so in our nudge paper, we proved we had some non-asymptotic results as well, right? We had the stochastic improvement result over first come, first serve. Is there any hope of proving stochastic improvement results with boost type policies?
The hope I have is in this chart, but actually proving it, I'm not so sure. It's possible, but
Okay.
I think you might have to do something like, you know, like for example, we our proofs right now apply for preemptive and non-preemptive. You probably have to stick to non-preemptive, some other details.
Sure.
And I think it seems harder than nudge, but it's maybe doable under similar assumptions like the sort of bounded density ratio.
Right. I mean, nudge had a pretty non-explicit version of that where it's like, well, there exists some threshold. So even
yeah,
the bar is low. I was more wondering if boost was better suited to this sort of thing than nudge was, but we can talk about this more offline.
That's a good question. I don't know.
Cool. Thanks. And great talk.
Thank you.
All right. So there's one more question on the chat message.
Okay. Is there any advantage for systems to deal with scheduling of light-tailed workloads than heavy-tailed workloads? So I guess okay, so I'm not totally sure what you mean by the question. If you mean by like, would you rather have a heavy-tailed workload or a light-tailed workload? Basically light-tailed every day. Just because it's less variable, and kind of the 0th rule of queuing is that delays come from variability. But As for like, whether we should be studying scheduling in heavy-tailed or light-tailed, there are, at least in computer systems, there's lots of scenarios where you have both. So there's lots of scenarios where you have like, network traffic that has heavy tails. A recent paper from Moore and folks at Google, showed lots of heavy tails in things like their job runtime distributions. But then you also have situations where you're scheduling at a lower level of granularity, and light-tailed assumptions are more important. So it is really important to study both. And I think it's also important to study things like Shane's question about slowdown is something that might be able to sort of give you an insight that applies to both. And I think that's the sort of, I think, open question that remains here. So I hope I answered at least part of that question.
Great. So yeah, Farzad seems to be satisfied with your answer.
You're welcome.
Okay. Yeah. So thank you once again for the fantastic talk. And so we will see 2 weeks from now for our last SNAPP seminar. So all right. Thank you again, Ziv, and thank you everyone for staying.
Thanks again for the invite. This was really fun.